Hi everyone. In this lecture, we're going to cover the second part of processor, the concept of pipelining in a processor. So the pipelining is an implementation technique in which multiple instructions overlap in execution. So before we focus on the pipelining in a processor, we look at the analogy of pipelining in a laundry system. Okay, for pipeline laundry, it means that we have the overlapping execution in the laundry process. Okay, we have, let's say we have 4 students here, Ali, Botak, Chin and Devi, A, B, C and D. And each student have one load of clothes to wash, to dry, to fold and to put away. So there are four stages for finishing one load of laundry. So for each student, they need to use the washer or the washing machine, and the duration for to use the washing machine is 30 minutes. And next, they will use dryer to dry, and the duration is about 30 minutes also. And folder, 30 minutes, and stasher for it takes about 30 minutes. So stasher is to put the clothes into drawer. Okay, in a sequential laundry, so let's say we have the time frame here, and we have the student, the task order. Okay, first Ali will do the laundry. So 4 stage: washer, dryer, folder and stasher. And then Botak, washer, dryer, folder and stasher. So after Ali finish, and then Botak will do his laundry. And then Chin, after Botak finish, then Chin and then Devi. So each student will spend about 2 hours to do their laundry. So after Ali 2 hours, and then Botak 2 hours, Chin 2 hours, Devi 2 hours. 2 hours. So altogether it is 4 hours. Sorry, altogether is 8 hours for 4 load of laundry. Okay, if we implement the pipeline laundry, so let's say Ali will do the washer, and then once Ali finish the first stage, the washer, Botak will do the washer stage. And then at the same time, Ali will do the dryer. Then once Botak finish the washer stage, Chin will do the washer, and then Devi, and so on. So we have a overlapping between stage here. So in this case, we reduce the time for all students to finish their laundry. So for non-pipeline, we spend about 8 hours, but for pipeline it's about 3.5 hours. So you can start from 6 p.m. finish at 9:30 p.m. Okay, it's the speed up is 8 is the hour for non-pipeline, and 3.5 is the hour for pipeline. So it can speed up 2.3 times in this case. Yeah. So pipeline laundry takes 3.5 hours for 4 loads. Okay, we save we save about 4 hours plus for our 4.5 hours here. However, pipeline doesn't have latency for single task. So you can see here, washer still take 30 minutes, dryer still take 30 minutes. It won't reduce, but and also each student will spend 2 hours to do the laundry. It won't reduce the time, but it just reduce the time to wait for all students, and will reduce the throughput for entire workload. So multiple tasks operating simultaneously using the different source. So if we want to implement a pipeline, so the stage for the task, each task must use different resources. So it means that this one will use a washing machine. This is dryer machine. If washing and drying in the same machine, it is not possible to put to make it this two tasks as a different stage. Yeah. And potential speed up is equivalent to number of pipe stage. So in this case, the potential speed up is maybe can be up to 4 times speed up if we have more workload, more load laundry here. So because in this example we only have 4 students, also let's say we have about 100 students, so the number of speed up between non-part 9 and part 9 is about 4 times speed up. Okay, the lesson of from part 9. Okay, let's say we have new washer, and this washer will take about 20 minutes, which is faster than the previous washer. And we also have new stasher, will take about 20 minutes also. It's much more faster than the previous one, 30 minutes. So, but dryer and folder still take 30 minutes. So in this case, still doesn't affect the whole process, yeah, because pipeline rate limited to the slowest pipeline stage, the dryer and folder. They still use 30 minutes, so we need to consider the longest or the slowest stage in this case. Okay, the same principle can be applied to processes instruction implementation. As we know, mixed instruction can be categorized into 5 steps or 5 stages. The first stage is fetch instruction from memory, and then second stage read the register and do the decoding for the instruction and execute the operation. Number 4 is to access the operand in data memory. And number 5 is to write the result into a register. So there are 5 stages or 5 steps so that in this case we can implement pipeline in the processor. Okay, let's say we have this scenario. Okay, let's say assume the time for stages is 100 picosecond for register read and write. So register read here, register write here. So 100 picosecond and 200 picosecond for other stages. So for instruction fetch, 200, for ALU operation, 200, and for memory access, 200. And we have instruction, let's say we have load word instruction, we have store word, and R format instruction, and branch instruction. Okay, for load word instruction, we will use all stages. Yeah, so we will use all stages because we need to fetch instruction, read and decode the instruction, and do the ALU operation, and access, do the data transfer from memory to the register, and then read, write to the register. Yeah. So we spend for this particular instruction, the total time to execute is 800 picosecond. And for store words, this kind of instruction will use all instruction stage except the register write, because this store word is to transfer the instruction from register to memory. So there is no register write here. So the duration for store word is 700 picosecond. And for R format instruction, so for R format instruction, as you can see here, of course we need to fetch the instruction, read the instruction, and decode and do the ALU operation. But for R format, there doesn't involve any memory transfer, data transfer between memory. So between memory and register. So this particular stage is idle. And for R format, we have the register write. So the total time for R format is 600 picosecond. And for branch instruction, So for branch instruction, it's going to use only 3 stages, the first 3 stages. So the total time is 500 picosecond. Okay, for this case, we are going to focus on the longest duration of instruction execution, which is load word. Yeah, for load word, the longest time is 800. So we are focusing on this section. Okay, for non-pipeline performance, so we have 3 instructions here. So this load words or 3 load words instruction. As we know from previous slide, load word instruction will use 800 picosecond. So we have 800 picosecond, and then once finish another instruction 800 picosecond, and once finish another 800 picosecond. So total 3 instruction is 2400 picosecond. So if we implement the pipeline, so we are the total time is 1400 picosecond. So we can see here, so once the first instruction finish instruction fetch, then the second instruction can do the instruction fetch, and then the third instruction can do the instruction fetch when the second instruction is finished with instruction fetch, and same goes to the other stage. Okay, so as I mentioned just now, pipeline stage time of a computer also limited to the slowest resource. So in this case, the slowest resource is 200 picosecond. Even though register write is 100, we still need to use the whole 200 picosecond here, yeah, because we are considering the slowest resource. So this is register read, this is register read, this is register read, and this one is register write, and register write. So the total time for 3 instructions is 1400 picosecond here. Okay, to calculate the pipeline speed up. So first, if all stages are balanced, so time between instructions, non-pipeline, divide by number of pipe stage. So in this case, we have 800 picosecond for time between instruction for non-pipeline, divided by 5 stages. So it is equivalent to 160 picosecond. So under an ideal condition and with a large number of instructions, so the speed up of pipelining can be equivalent to number of pipe stage. In this case, we can achieve up to 5 times faster between non-pipeline and pipeline. However, there are some consideration we need to take notes that the stage may be imperfectly balanced, as we can see just now. Register write or register read only 100, but the other stage is 200. So it is unbalanced. And also we need to consider pipeline involves some overhead. And it is not it's impossible to get this ideal speed up for pipeline. Yeah. So if we want to calculate the pipeline performance from the previous example, so we can see that for non-pipeline is 2400 and for pipeline is 1400. So the speed up is 1.7 times, yeah, pipelines versus non-pipeline. Okay, so this is only 3 instructions. Okay, let's say we have another, we add extra 1 million instructions. So if we have 1 million instruction plus the 3 instruction that we have just now, so to calculate the total execution time, so 1 million times 200, 200 is the duration of each instruction, each stage. Yeah, for one stage is 200, so 1 million times 200 plus 1400. So this is the 3 instruction that we calculate just now. So this is the total time for pipeline for 1 million and 3 instructions. So for non-pipeline, 1 million times 800 plus 2400. So this 2400 is the 3 instruction that we have just now. So this is the total time for non-pipeline. So the speed up, in this case, the speed up is the total time of non-pipeline divided by the total time of pipeline and equivalent to 4 times. So we can get up 4 times speed up between pipeline and non-pipeline. Okay, next we're going to look at how to design the instruction sets for pipelining. Okay, as we know, there are 5 stages and 1 step first stage. So we have instruction fetch, and we can use this abbreviation IF. Instruction decode and register rate, we use the abbreviation ID. And executes operation or calculate the address, we use abbreviation EX. And access memory operand, we use the abbreviation MEM. And lastly is write result back to the result. So we use write result back to the register. So we use abbreviation WB. So for single cycle data path, we can see this is the data path and the control. So we have a program counter, memory instruction memory, and this is data memory. We have the registers here, and we have the ALU control, and we have the adder to add the instructions, and we have the multiplexer here. So this is the single data path. So the first stage in the instructions execution, first instruction fetch, decode, register rate. So mostly in this part, and we have executions in this part, particularly in this ALU part, and then memory, data transfer between memory register memory. So in this part, and then we have the last stage is register write. So this is for single cycle data path. So if we want to implement the pipelines, so we need to put the new registers here. It is called as pipeline register. So between the stage, we need to have one registers to keep the information between stage. Yeah, for instruction fetch, so one register to keep all the information for this particular stage, and then we have the one register here, and we need to have another register here and one register here. Okay, so based on this abbreviation IF, ID, EX, MEM, and WD, so this is the register. So we can name the register based on the abbreviation. So this register is for to keep the information for IF and ID. So IF is information fetch, ID is register read and decoding. So we have ID EX execution, and then EX MEM and MEM WB. Yeah. So we have the extra component here. We call it as the register, extra register to keep the information between stages. So if we have the load store instruction, yeah. So if for load store, so if information instruction fetch for load store, so we have information fetch, and then the information will be kept in this register. And then in the decode, so this is where the information for this particular stage will be kept. So we have the information keep in the register, and also the information used in the stage, and also the information here. And same with the execution. So we will use the register for keep the information for the stage, and then use the actual ALU here for execution process, and then this one for memory access, and lastly for write back to the register, it is quite different, because this one is actually to write back the information to the register. The results from the calculation here will be right back to the register. So you will have the information from whatever the results is transferred from this register, from this pipeline register to this pipeline register, and then this data information will be returned to this register. So this is how the pipeline is implemented in a processor. Okay, to summarize, the pipeline improves the performance by increasing the instruction throughput, where we can execute multiple instructions in parallel. And there are some complexity we need to consider when we are implementing the pipeline. Okay, that's all for the lecture today. Thank you very much.